Welcome back. Today we're going to be talking about characteristics of quadratic functions. All right, the first thing we need to cover is how we can identify a quadratic function. So a function is said to be quadratic if it's of the form y equals some number times x squared plus some number times x plus some number here, where a, b, and c are real numbers, right? So real meaning that they could be rational or irrational numbers. And what's really important is that what we call the leading coefficient here, a, it's the coefficient of the x squared term. This cannot be equal to 0. Okay, and the quadratic equation in this form is called standard form. Right, it's in standard form where it's represented as something times x squared plus bx plus c. What's implied in this sentence is not only that a can't be equal to 0, but b and c could be equal to 0. So for instance, y equals x squared, the parent function, is a quadratic in standard form because we have 1x squared plus 0x plus 0, where b is equal to 0 and c is also equal to 0, and that's totally fine as long as the leading coefficient here, the coefficient of the x squared term, is not equal to 0, then it's a quadratic function. So for instance, if we had to identify if a, b, and c are quadratic or not, well, this right here, if I were to add the a term, it would be 0x squared, okay? And so the a, meaning I could add this, remember this right here, this, what I've just written down, 0 times x squared is just equal to 0. So I'm allowed to add that on to the end here. Now, this would make, so this right here is not a quadratic equation because if I added 0x squared, well, a would be equal to 0. Another way of just looking at this is, look, this is a linear function, right? The highest exponent I see on x is 1 right here. So this would just be a line with a y-intercept of positive 20 and a slope of negative 2. This would not be a quadratic equation. It wouldn't form a parabola when we graphed it. Here, now look at the standard form of the equation right here. The x's and y's are on different sides. So here I would subtract 3x squared from both sides to get it into the standard form right here. And I'd be left with y equals negative 3x squared minus 4. And this is perfectly fine. Here, a is equal to negative 3. B is equal to 0. There's no coefficient, there's no x term. So, oops, that would be 0 right here. And C, the constant, is equal to negative 4. Okay, again, the x's and y's are on the same side here. So let me go ahead, let me add y to both sides. And we'd have 2 plus 4x squared is equal to 4x plus y. Let me subtract 4x from both sides just to get it in standard form. We have y is equal to, let me rearrange this so that it's the 4x squared is in the first term, minus 4x plus 2. And remember, I can use the reflexive property, which flips around the things around the equal sign. Y is equal to 4x squared minus 4x plus 2. Okay, so this is a quadratic equation because here we see a is 4, we see b is negative 4, and we see c is 2. Okay, so it's a quadratic equation in standard form. So this is a quadratic equation. C and B are quadratic equations. A is not a quadratic equation. Okay, some characteristics of quadratic equations is that, and of parabolas, is that they have either a maximum or a minimum value. They can't have both. So if a is greater than 0, what we know about it means that if the leading coefficient is greater than 0, then the parabola opens upward, right? And if it opens upward, then the y value that the vertex is called the minimum value. So here's an example of a parabola opening upward. The y value of the vertex, or 0 in this case, is called the minimum value of the function, meaning that is the smallest value that the function, or the y value, ever gets to. So if a is greater than 0, the function has no maximum value, meaning it actually goes up into infinity for the function values because the y gets increasing on both branches here. If the parabola opens downward like this, if a is less than 0 and the parabola opens downward, then the y value of the vertex represents a maximum value for the function, meaning that is the highest number that the function gets to. This is the highest y value that the function gets to. So this is called a maximum value. And if it's opening downward, there's no minimum value because both branches go off to negative infinity, right? So, and at the same rate. So they both go to very, 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 very small values of y. So we don't say that there's no minimum value, all right? So in order to find the maximum minimum value, first you need to know the a value, right? Is it positive or negative? So here your a value was -1, so we know the parabola opens downward. And here the a value is 1, so we know the parabola opens upward. So you need your a value, and then you need your vertex to determine if it's a maximum or minimum. Okay, so let's practice with this. So A and B are fairly simple because we can see that the parabola opens downward. We're given the graph, not the equation. So here we know that this is a maximum value because it's opening downward. So it's the vertex is at 1, 5. So the maximum value is the y value here, which is 5. Okay. Here the parabola is opening upward. So here the vertex is at -2, 3, 4, 5. So -5. It's opening upward, so we have a minimum value of 5. Oops. Minimum value of 5 here. Oh, -5, rather. All right, and there's no maximum value when it's opening upward. Now, C is of the form where we can easily pick off its vertex, right? So when it's in this form, we know the vertex is the opposite of the x of the value inside here, and the face value of the value outside, right? Because we know about horizontal and vertical shifts. So here's the vertex. We know that the a value is positive here because if this is going to end up being the leading coefficient here. Or we also know from our compression and stretching lesson that this value outside is going to determine whether it opens up or down. So here, this is opening upward, so that means that it's a parabola that looks like this. So the vertex is going to be the minimum value. So here, the minimum value here is -6, and the maximum value is none. Okay, again, here the vertex is 4, +5. So it is, and this is opening downward, so this is going like this. So its vertex is going to be its maximum value here. So the maximum value is 5, and the minimum value is none. Okay. Now, we have talked about this before, and we've talked about it when we've had quadratic equations and we've set them equal to 0. But when we're given quadratic functions, what we call the zeros of a function is the value of x that makes the value of the function 0, right? It makes sense because it would be the 0 of the function. It would make the y value 0. When we talk about values of functions, by the way, what we're discussing is the y values of the functions. So the zeros of a function are the x-intercepts, right? Because all on the x-axis, y is equal to 0. In fact, that's another equation that we have with the x-axis. So we're looking for the x-intercept, or the zeros of the function. A quadratic function can have 1, 2, or no zeros. So here's some examples of this situation. We have the first one here has 2 zeros, or 2 x-intercepts. This next one here just goes up to the x-axis and bounces on it, and then it comes back down, right? So it has 1. And then here, these have no x-intercepts. And what I want you to recall from our conversation in class is that there are no real number x-intercepts, but there are imaginary values that are zeros for this function. And you'll talk about that in Algebra 2. Now, if I needed to determine the zeros of this function here, I can just pick them off the graph and then check my answer here. So here my zeros are -1 and +2. And here's my equation. Now, if I were just given the graph of the parabola and I were asked to find the equation, what I could actually do is work backward from the zeros, because I know that these came from 2 separate equations that I set equal to 0. So my function would be y is equal to x plus 1 and x minus 2. Notice that if I put 2 in here, I would get a 0 for this factor. If I put a -1 here, I would get a 0 for this factor. Both would lead to a y value of 0. And when I multiplied these out, I would get, here would have the x squared. The sum of these two would be -1, so it would be -x, and the product of these two would be -2. And that's what gets me the equation up here. So if you're ever asked to work backwards from the quadratic function, or the graph of the quadratic function to the quadratic equation, then you can do it that way. Okay, here I can check into this equation here. So let's check the -1 first. So y is equal to -1 quantity squared minus a -1 minus 2. Notice that this minus is coming from the quadratic equation. This -1 is coming from the substitution of -1 in for this x. So we have y is equal to 1, and this would end up being plus 1 minus 2. And that would indeed get me 0. Okay. This next one means it's a repeated root. So this is 1 right here. Okay, now what that means is that the original quadratic equation looked like x minus 1 quantity squared. So again, if I put 1 in there, I would get 0. So another way of looking at it is x minus 1 times x minus 1. So if it has a single root with multiplicity of 1, or sometimes, of multiplicity of 2, sometimes we call that a repeated root. What that is it's the same binomial that's been multiplied by itself. Okay, now, actually, this one has a narrower bowl here, so it's not just this. There would be a number on the outside, and we could determine that by finding a value here, 2, -1, 2, -2, and plugging it into the function, if we wanted it, if we wanted to. So it's something like this, but there's some a value here that we haven't worked out yet, and we could do that. I've shown you how to do that in the previous lesson, so I won't go through that right now. All right, so let's make sure that this 1 right here is a root just by checking it. So we have y is equal to -2 times 1 squared plus 4 times 1 minus 2. So we have y is equal to -2 times 1 plus 4 minus 2, which is -2 plus 4 minus 2. So -2 plus 4 would be 2, minus 2 would end up being 0. So this one checks out too. So it would be 0 equals 0 at the end. Okay, now this right here has no real roots, meaning it doesn't cross the x-axis on the real number system. So here we can't actually check to see if a root we can't actually pull out a root from the graph here to check it. But what we can see is that if I set the left side equal to 0, what would end up happening, I try to solve it this way, so I'd subtract 1 from both sides. -1 is equal to 1/4 x squared, and if I multiplied each side by 4 in order to try to solve this equation for x when y is set equal to 0, I'd get -4 is equal to x squared. And you'll notice here that there's no number that when I square it, I get a negative number. So here, this also indicates that the roots of this quadratic equation are imaginary numbers. In other words, we can't see it on the, remember, the x and y that we see here are these are real numbers that we're graphing on the x and y plane here, so we won't be able to see imaginary roots if they show up, okay? Finally, we talk about axis of symmetry. So an axis of symmetry is, we've talked about this before, it's the line by which if you folded the parabola over, it would lie directly on top of itself. One branch would lie directly on top of the other one. So the vertical, it's also the vertical line that divides the parabola into two symmetrical halves. This is called the axis of symmetry. This axis of symmetry passes through the vertex of the parabola, right here. And you can use the zeros of a function to find the equation for the axis of symmetry. Now, what I want you to recall is that vertical lines have an equation that's of the form x is equal to some number, okay? Because it's what we know all about the points. What we know about all the points on this line is that the x values are equal to the same number here. The y values all change, but the x values stay the same. So here, if a quadratic function has only one root, then the axis of symmetry is going to be the x value of that vertex. So it's x is equal to 3. Okay, because that's the point where so it's always the x value of the vertex. Another way of saying that is what I just said. If there's two, if you've been given the two zeros, okay, then what you do is you take an average of the two zeros. So here, or average of the x values of the two zeros. So you take -4 plus 0 divided by 2, as you see this in the calculation up here. So -4 divided by 2 is -2. So that's going to be, essentially what you're finding is the x coordinate of one of the points in this line, but since it's a vertical line, it's going to be the x-coordinate of every one of those points. So that's going to be the equation of the line. Another way of determining it is if you look at the vertex here, which would be -2, -4, it's always the x value of the vertex is the line of symmetry. Okay, so if you're given the roots, it's the average of the two roots. Or if it's a single root with multiplicity 2, it's the x value of that root. But if you're given the two roots, it's the average of the two roots. If you're given the vertex, it's really easy. It's just the x value of the vertex. Okay, so that's all the characteristics that we need to go over today. We talked about maximum and minimum values, we talked about roots, and we talked about axis of symmetry.